9, 3, 4, 7 divided by the square root of 50. Negative 0.9531. Yeah. I had Mr. Rich stop in, so I wasn't sure. I lost my train of thought there. Negative 0.953. That's my t-score. Let's go through and find, it's negative. Our value, so this is how we do this, ready? TCDF, negative 999 to negative 0.953. And when I do that, well, let's do it. So second dister, TCDF, negative 999, negative 0.953, degrees of freedom 27. I get 0.1745. Now, if you remember, in our hypothesis, we said not equal to. So you have to take this and multiply times 2. Okay? So if I hit that and multiply times 2, we're going to get 0.349. So my p-value equals 0.349. So let's conclude, okay, with a p-value this high, we fail to reject the null hypothesis. There is not enough evidence to say the width of ice cubes is not 29.5. Okay? What type of an error could I have made? What did I do? I failed to reject. So when you fail to reject and you make a mistake, that's called a type 2 error. Okay? All right. Look at this. This is very common, guys. This next part is very common because you know what they're doing? They are tying in confidence intervals with significance tests. Okay, they're tying it together. So it says interpret the confidence interval. So we're talking about that same problem that we just did. Okay, we are talking about that same problem. So with that problem, let's see what it says. 29.4609. 29.4609 to 29.514. 29.514. So it says to interpret the confidence interval. Yes, that's what we want to do, right? We like that. I am 95% confident that the interval from 29.4609 to 29.514 captures the true mean width of ice cubes. Okay? So we interpreted the confidence interval. Would I make the same conclusion? Well, let's look. Does 29.5 fit in there? Yeah, 29.5 fits in there. Okay, so we just see how they say it, but like I said, 29.5 fits in there, so we're not going to think anything strange is going on. It's plausible. We don't have convincing evidence that the mean is not 29.5. Okay, and then it says interpret the confidence level. That's the one we don't like to do. Okay, and we would say in repeated samples of size 50, in repeated samples of size 50, 95% of the intervals, okay, that we obtain for the mean width of ice cubes would contain the true mean width of ice cubes. Okay, so the difference between confidence level, we talk about that size 50. 95% of our confidence intervals of size 50 would contain the true mean width of ice cubes. All right? So I want you guys to do, on page 577, okay, take a look at the check your understanding on page 577. So please do that now. And then we'll see if we can finish this. I think we can. I have 20 minutes till my next class. I think we can. So let's pull up this problem. The health director of a large company is concerned about the effects of stress on the company's middle-aged male employees. Yeah, that's me right now. According to the National Center for Health Statistics, the mean systolic blood pressure for males 35 to 44 years of age is 128. The health director examines the medical records of a random sample of 72 male employees. Wow, what a nice sample. 72, we don't have to worry about normality there, do we? The mini-tab output below displays the results of a significance test and the confidence interval. Do the results of the significance test allow us to conclude the mean blood pressure for the company's middle-aged male employees differs from the national average? Justify your answer. So I'm going to give you two reasons here. One, here is 0.275. So I don't think there's anything strange going on. To me, that's evidence that it's not that different, okay? It's not going to be different. And the other thing is, 128 would also be caught in that interval. So those are the two things, the p-value for the significance test and 128 being in the 95% confidence interval. Interpret the confidence interval in context, okay? So we are 95% confident that the true mean systolic blood pressure for the company's middle-aged male employees is captured in the interval 126.43 to 133.43. Okay? Explain how the confidence interval leads to the same conclusion. 128 is in the interval. We just talked about this. 128 is in the interval. Okay? And with a p-value of 0.275, okay, that leads us to say there's nothing strange going on. That we can't say it's different. Okay? We think it's going to be the same. We think that's reasonable. Okay? Here we go. Let's finish the game. Let's finish the game. A section I thought I was never going to get to. So, inference for means, paired data. Paired data. Comparative studies are more convincing than single sample investigations. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals results in what's called paired data. You analyze paired data by first taking the difference within each pair to produce a single sample and then a one sample T procedure. So I would underline that, okay? I would put a little underline under that, okay? We're using, this is paired data. Paired data is still a one sample T test, okay? Or one sample T interval, or however you want to say it. Only the distribution of differences needs to be approximately normal. So, is the express lane faster? Okay? So it says, for their second semester project in AV Statistics, Libby and Catherine decided to investigate which lane was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during a week, went to the same store, and bought the same item. However, one of them used the express lane, the other used the regular lane. To decide which lane each of them used, they flipped a coin, random. If it was heads, Libby used the express lane and Catherine used the regular lane. If it was tails, Libby used the regular lane and Catherine used the express lane. They entered their randomly assigned lanes at the same time and each recorded the time in seconds it took to complete the transaction. So it has the seconds here and it has the transaction. Okay? So what we have to do is we have to come up with a null hypothesis. So we are going to perform a significance test to see if there's convincing evidence perform a significance test to see if there is convincing evidence that the express lane is faster. Okay? A null hypothesis, an alternate hypothesis. Okay? So, what I'm going to do is I'm going to think of how what I want to talk about, what my difference is going to be. So, let's say that I am going to call the mean difference to subscript is equal to regular minus express. Okay, that's my mean difference. And we're going to say here in our null hypothesis that there is no difference, right? That's what we do for a null hypothesis, okay? We always say that there's no difference. And now, what would we think? What do we think? We want to see if the express lane is faster. So my alternate hypothesis would be that the mean difference is greater than 0, because that would mean that regular is bigger than express. Okay? Really good job right there with our statements, a really good job. Okay, so my plan, A1, sample t-test for means. It told me to do that. Okay, it told me to do that. Random, normal, independent. Random, we know it was random, right? They flipped the coin. Okay, let me see how they explain that. But they flipped a coin, so that's part of our random. So two things happen, okay? Random times were chosen. Okay? A coin was flipped to choose which lane you picked. Okay, so there was two things for random. Normal. Well, I think we're going to have to probably do a graph for that one. So let's go to our calculator. Let's go to our calculator. Let's enter in all of these things. Okay? So we go to, I'll show you how to do this, ready? So we go to our calculator and we go to stat. Whoops, turn it on. Stat, we go to edit, and I clear out that first one. And I'm going to enter these numbers in. 337, 226, 502, 408, 151, 284, 150, 357, 349, oops, 257, 321, 383, 565, 363, 85. Okay, and then I gotta go to the top again and do the same thing over here. 342, 472, 456, 529, 181, 339, 229, 263, 332, 352, 341, 397, 694, 324, 127. Okay, now, I have to get an L3. Okay, now in my L3, I want that to be, we said it was going to be regular minus express. So when I label this one, I'm going to hit second L2, so 2, minus second 1, which is L1, and that gives me all of my differences. Okay, that gives me all of my differences. And now what I've got to do is I've got to get a graph for all those differences. So I go to second step plot, I turn it on, I go down to X list, and let's make this L3, enter, let's hit graph. Obviously doesn't fit my data, okay, so I'm going to hit zoom 9, okay, and it looks reasonable. There's my graph, okay, it looks reasonable. I've got some negative values, so I would go and try to draw this graph. Again, let me show you the process. So the minimum value is a negative 94. So I'm going to make a number line and make this negative 100. Let's see what the values go to. So I go to negative 94, to negative 17, to 30, to 95, to 246. I guess I'll go by 50s. Negative 100, negative 50, 0, 50, 100, 150, 200, 250, 300. Kind of a big graph. I guess I could have went by something else. I don't know. So the first one, the max is at 256. So the max is here. This one was negative 94. I think the other one was negative 17. 95 and 30. So 95 and 30. Okay, we make our graph. Okay, since the graph, you'd say something like this. Ready? Listen to me. I'm not going to write it down. I already wrote it. Since the graph shows no outliers or strong skewness, we can use the normal approximation. Okay? How many do we have here? 15? And then I'm going to say 15 is less than or equal to 10% of all customers using the lanes in the grocery store. Okay? Pretty good job there. Pretty good job again. Got ourselves in the back a little bit. All right, next one. So for the next one, the do step. So we have to go to our calculator, and we've got to do second trace for calc, no, stat calc, yes, one variable statistics, but I got to do it for my L3. So it looks like I get 42.67 for my X bar. So for my T value, it's going to be 42.67 minus 0. Divided by the sample standard deviation, which is 84. 84 divided by the square root of, what do we have, 15 scores? So if it's 15 scores, yeah. So I'm going to have 42.67 divided by this mess. Let's do this. Let's do this. See if they do that in the book for me. Are they good? They do that? They do. They give me 1.97. Trying to finish this before I end my block. So if that's 1.97, we're going to do T, C, D, F. 1.97 to 999.